Okay, this will be an attempt at an overview for the BJX2 ISA's WEX and Jumbo encodings. So yeah, it'll be an attempt to explain the it'll be an attempt to explain the basic idea of the WEX and Jumbo encodings in BJX2, and as can be noted, this is based around my newer 2D iteration of the ISA, or ISA variant. Encoding details have changed since earlier ISA variants, so some of this stuff is a little bit newer in terms of encoding. So yeah, wide execute. This is a fairly important flag for the encoding of instruction bundles, and an instruction marked as WEX is followed by more instructions within the same bundle up to an implementation defined limit. Currently this limit is 3 in my current cores. There are various trade-offs for why 3 seems to be a reasonable limit, but some of them have to do with like register ports and other factors like that, and going like narrower like 2, it means that some combinations of instructions aren't really encodable, and more than 3 doesn't really have much advantage, but has increasing cost, because the cost is itself a little bit non-linear, so going from 3 to 4 is not super cheap. So yeah. So yeah, it's terminated. A bundle is terminated by an instruction that's not marked as WEX. So that would mean, like, yeah, any normal scalar instruction will implicitly terminate an instruction bundle. Each instruction within a bundle is executed in parallel with any other instructions in the bundle. It's basically, yeah, the main way it's defined. And no logic is needed or used on the CPU to infer whether or not bundles are well formed. That is part of the point of this, because basically because it's not a super scalar, but it's also not a pure scalar either, because it can execute operations in parallel, but yeah, it avoids some of the cost of a super scalar in this case. Yeah, as noted, yeah, this is cheaper and simpler than a conventional superscalar. There's no need to figure it out in the CPU, and thus less hardware cost is needed. It's also immediately visible during fetch, avoiding latency and uncertainty. This would be the latency and uncertainty of needing to basically fetch and then decode multiple instructions before it's possible to infer whether or not they can execute in parallel, and so on. So in a superscalar, you would need to figure out some point later yeah. In a superscalar, you'd need to figure out sometime later whether or not they could be executed in parallel. This design does have better code density than a traditional VLIW. Doesn't waste space encoding NOPs, and this also helps performance by reducing the required cache pressure or instruction cache pressure. Basically, in a traditional VLIW, you'd have fixed size instruction blocks, typically 128 bits or so, and you would divide them up into multiple instruction words. So you either have to use up all of those instruction words by executing instructions in parallel, or failing that, it's typically necessary to fill up any unused spaces with NOPs, and that can potentially significantly reduce the code density, which is detrimental. However, binary code is less general if compared with something like a superscalar. The number of slots or lanes and what is allowed to be done within them needs to be known at compile time. Binary code may not run efficiently or at all on a different core from what it was compiled for. Both of these are limitations shared with VLIW designs. But I tried to work around them some in the design, but I've still not been able to completely avoid these issues. Scalar code will generally work on a wider core, and if used with care, code generated for a wider core can work on a narrower core, but the feature sets aren't necessarily one-to-one between cores, so it's not really exactly guaranteed that code intended for one core will work on another. A partial workaround is profiles. So a profile would set a subset of features which are required for the core to support, and it potentially allows falling back to scalar execution or a more limited subset of the ISA in certain cases. So it's basically, if you try to generate code for a core wider than what the core implements, then it will fall back to scalar mode and run it at lower performance, but it can potentially allow it to still work. It won't necessarily work though if the code is using instructions or other features that aren't actually supported on the target. So it's kind of limited in that sense. Another possible workaround is specialization. So programs could be distributed in a higher level immediate form, and then basically an ahead of time compiler would be used to produce the actual binary. In this sense, they would be something more like a .NET binaries or Dalvik or something. But preferably an alternative to those would be used, because both those VMs are kind of not really particularly well suited for languages like C or similar, where presumably languages like C and C++ would be the primary languages you'd want to support with something like this, so it would make sense to support those. But just sort of a higher level intermediate form which could support C. This would probably be in either as a stack-oriented bytecode, or maybe like a form of 3 address code. both of those are supported. Yeah, my compiler currently has support for like serializing code in both of these forms, but it's not really yet, not really in a form that's all that suitable as a binary distribution format. More it's being used for things like statically linked libraries and similar. But in premise, something similar could be adapted. Predication and PrWEX. So some instructions may be predicated, as in, yeah, these instructions will be executed or not executed based on an external condition flag, and in some cases it may be cheaper to execute instructions as NOPs or no-ops rather than branch over them. This is because a branch will carry a certain constant overhead. In my current course, it would basically be about 2 cycles if it's predicted correctly, and about 6 cycles if it's mispredicted. And but in short branch or for short sequences, it might be cheaper to just have the instruction be executed as a NOP rather than branch over it. The reason it's like not always preferable to predicate is because if the sequence of instructions that's being predicated becomes overly long, then the executing the unused parts as NOPs will end up costing more cycles than branching over them would have. So it's a trade-off. Yeah, some instructions may be both predicated and WEX. Yeah, these are the PrWEX blocks. This allows predicated instructions to execute in parallel with other instructions, and only a subset of the instructions may be encoded this way. Partly it's because, well, there's only so much encoding space in an instruction set, and so it's the main instruction blocks can be encoded this way, but some other ones that generally can't really be executed in WEX mode are generally left out of this grouping. But it will be pointed out later. Jumbo prefix. This is decoded similarly to a WEX instruction in that, well, yeah, it uses up slots, and these slots will behave as if they were NOPs. In this sense, it's kind of similar to just a WEX sequence with a bunch of NOPs in it, except like they actually serve a purpose. For now, Jumbo implicitly requires WEX support. Well, it's because it basically uses the WEX mechanism to actually decode it, so kind of why it depends on it. An implementation that was based around a scalar core would actually have to have special case logic to either decode the instruction as multiple steps and then glue them together after the fact, or it would have to basically detect it and then decode and execute it as if it were a single larger instruction, which isn't actually how it works in the current implementation. So its usual main purpose is to expand the size of the immediate field in the following instruction. So, for example, sticking a jumbo prefix on an instruction that expects a 9-bit or 10-bit immediate will produce an instruction with effectively a 33-bit sign extended immediate, and sticking 2 jumbo prefixes onto a 16-bit or onto an instruction with a 16-bit immediate will produce one with a 64-bit immediate. Use in most other cases is reserved, and yeah, it's partly because I might potentially use these for future ISA expansion later. One possibility is using a jumbo prefix in a 16-bit instruction as a sort of 48-bit opcode space, but I've not yet decided on whether or not to reintroduce 48-bit instruction formats, which were something which this incarnation of the ISA is sort of lost. But partly that was because they created problems with WEX, and also because I needed to reuse the encoding space for something else. So the assembler syntax is noted, consists of multiple instructions, potentially with bars stuck between them, which indicate which instructions are executed in parallel. So yeah, the bar separates instructions to be executed in parallel, and the slots are numbered in reverse order. Yeah, this can be seen here. So final instruction is always lane 1, which is lane 1 is the main lane that would be used for scalar instructions. But in the case of WEX or parallel sequences, well, they're in reverse order. So one with only 2 instructions would have 2 and 1, and then a scalar instruction implicitly is only 1, and a 3-lane instruction or sequence is always 3, 2, 1. This layout or this ordering is basically matches the same order as the machine code, and it's the same as in the assembler. This is partly for implementation reasons, because it makes it easier to made it easier to implement the assembler, whereas if I had to put it in 1, 2, 3 ordering but have the same coding, it would be necessary for the assembler to decode all 3 or decode the instructions and then flip the order around and then re-encode them, which is more complicated. And so yeah, a question mark followed by a T or an F indicates that an instruction is predicated. May or may not be obvious, but the T or F indicates whether or not the instruction is to be executed if the predicate flag is set to true or false. So if the T flag is set and it's a T instruction, then it will run, and if it's and if it's set and it's a false instruction, then it won't run, and vice versa. In the PrWEX case, you can use basically predicated instructions with the bar here in order to make sequences where one of the sub instructions will execute and the other one will not be executed, but in parallel. You can also do multiple instructions that have the same predication, in which case they would be either executed or not executed, or so on. Or to have 3 instructions. It's not really specific on how many instructions you have exactly or how they're predicated, but this is just an example. So the destination is on the right hand side, and this notation, and with parentheses indicating memory memory operands. But as noted, it's only for load stores because BJX2 is a load store instruction set. So yeah, it's not like x86 or anything, or you can just reference memory on something like an add or similar. But so yeah, but it's just loads or stores, but parentheses will indicate memory operands. And on the right hand side, that's basically similar to the AT&T syntax that GAS uses, or so on. Okay, so now on to the instruction coding. It's noted it's organized in terms of 16-bit words as the basic unit. But the high bits of the instruction indicate whether or not it's a 16-bit instruction or a 32-bit instruction. So if the top 3 bits are anything other than 111, then it will be a 16-bit instruction, and these are pretty much always scalar instructions and thus can't really be used as part of a WEX sequence. Yeah, and then anything within the E block is treated as a predicated instruction, or it's PrWEX. So PrWEX is the special case. So as noted, the basic unit in all these ones is 32 bits. PrWEX it makes the bundle longer, but and the instruction itself is still considered as being 32-bit. And as noted, they alternate between true and false blocks. So true, then false. These two are true and these are false, but it's all the same bit in this case, so it's, yeah. And the F block, that's all the other 32-bit instructions. So within the F block, so as noted, the second digit here corresponds to this X here. So, and this is the first 16-bit word, and this would be the second 16-bit word. And which ones are the letters that are uppercase and look like hexadecimal characters? Well, those ones are hexadecimal characters. So yeah. And if they're not a hexadecimal character, then they mean something else, or if they're lowercase. So yeah. The FO block is most of the basic instructions, mostly 3-register and 2-register forms. There are a few exceptions, but for the most part it's 3-register and 2-register. The F1 block is used for load store instructions, generally with a 9-bit displacement. The F2 block is used for 9 or 10-bit immediates, well, with the exception of WEX and other things like that, but get to that later. And yeah, F3 and F9 are reserved for probably future ISA features, but they're not used yet. Yeah. So the F4 to F7 blocks, they actually have, apart from being in a slightly different range, they have this exactly the same contents as the FO and F3 blocks. So the same basic pattern repeats and the same basic instructions are contained in both, just the differences in this range they're interpreted as being WEX. Going back to the previous one, it's basically the same idea with these predicated blocks, as they will actually represent the same logical instructions, just the which range they're in the terms of their high order bits indicates how they behave and stuff. So there's also an M16 block, which has, well, a single register and a 16-bit immediate. So that's its main defining characteristic. Then there's also a few instructions which their main purpose is essentially to load a 25-bit sign extended immediate into register R0, where R0 is implicitly used as a context, or as a constant register for some instructions. Except loads and stores, where it has other additional meanings. So FC and FD repeat F8 and F9, but are marked as WEX. This part is different from before, where before, like, F9 was effectively the same as what FC is now, and F9 and FD as distinct blocks didn't exist yet. But this spot here is where the 48-bit instructions previously went, but I ended up dropping those and moving F8 into here and stuff. That was mostly for encoding reasons. Yeah, mostly to try to make the encoding like somewhat consistent. FE is the jumbo prefix, and it works by adding 24 bits to the following immediate. Yeah. Suspect I'm having a bit of an issue with allergies right now, so what's going on there? But yeah, so adds 24 bits to the following immediate, and yeah. So yeah. Then FF is also reserved for jumbo, but it's not actually used yet. Instead of adding to the immediate, this one might actually be used as an add more opcodes feature. Like, possibly adding instructions that are something other than just, the same instruction but with more immediate bits. So yeah, instruction length, it's not that complicated in terms of implementation. So if the high 3 bits are ones, then it's 32 or more bits, otherwise it's 16-bit instruction. As noted, it's in the basic encoding, it's either 16 or 32, but the 32 plus is because you can have WEX and Jumbo prefixes, which potentially count as longer instructions, but yeah, depending on how you count it. So so yeah, WEX, PrWEX, or Jumbo are needed for longer than 32 bits. And so, as noted, these are the ranges which encode these cases, and for bit patterns, 1Z, 1Z, or O1Z1 basically corresponds to a pattern, which means that it's either a WEX or a Jumbo. That's bit 12 is basically the bit that selects between the E or F block, so that's why it's included here. So this would be the F within the F block, and this one would be within the E block. So there's a latency of around two lookup tables or 2 LUTs for detecting this case, and stuff, but that does require getting a little bit clever to get it down to 2 LUTs, but I have determined that it basically can be done. A group of n-1 ops needs to be considered for maximum length, or for a maximum length bundle of n. In the case of 3, that means we can look at the 2 bits from 2 different instructions and then be able to tell whether we're looking at a single scalar instruction or 2 or 3 element Jumbo or WEX form. Once we know the length of the bundle, we can of course advance PC to the next position for the next clock cycle. But and as noted, if we actually use a case block which takes the current PC into account and then combines it with the length of the bundle, we can actually figure out where the next instruction will be without needing to use a dedicated adder or similar. So sidestepping an add is potentially saving a little bit of latency and thus potentially better for timing. Instruction formats have the range of 16-bit formats, which we generally have the Z for the opcode bits, but that'll be typically in the high 8 bits of the first word, and then usually the N and M, or destination and source registers within the low bits. So might have 2 registers for an 8-bit immediate, or a 4-bit immediate and a register, or in some cases an 8-bit immediate and a register, and so on. Consistency is difficult. As much as it might seem like say more consistent if you were to shift everything over 4 bits and then put one of the Z's over on this side, which is another possible encoding, well, then you just end up makes one case more consistent. Like, you can possibly keep n consistent between these instructions, but then other cases are less consistent, which is kind of problematic. So part of the instruction set design is trying to weight the possible options to see what's more consistent, and or whether the consistency will actually buy anything enough to justify the cost of changing something. sometimes it pays off, other times it's, doesn't actually make that much difference, and so it's wasted effort and breaking binary compatibility for nothing and so on. But yeah, for most of the 32-bit formats, it's generally a layout something like these. So it's generally the N and M registers are in here, in roughly the same places in the 16-bit instructions. But we might put the opcode bits over in the second word. The third register and also the E block will be also in the second word. The E block basically being where some of the bits are, or some of the register bits are put to allow for 32 registers rather than the 16 that would otherwise be possible with just a 4-bit register field. Yeah, but it's at least, semi-consistent to what extent I could get it being so. And so there's 3 and 2 register instructions. Not much of note there. 20-bit instructions, which are actually typically like things like branches. So there's some branch instructions that have a 20-bit, well, displacement actually, but yeah. And there's also load and store instructions with a 9-bit displacement. There's also load and store instructions in a 3-register configuration as well, and in 2 register, so it's not exactly lacking. And there's 9 and 10-bit immediates and a few instructions with 16-bit immediates. It's noted Jumbo is basically exactly the same instruction as if it were by itself, just with the Jumbo prefix tacking 24 more bits onto the immediate. So a little, basically just a relatively minor set of decoder hacks. So a lot of the instructions will accept a single Jumbo prefix, which causes them to have a 33-bit immediate, whereas the F8 block instructions will take 2 Jumbo prefixes and gain a 64-bit immediate. It's currently not allowed to, use an F8 block instruction with only a single Jumbo prefix, or to use an F2 block instruction with 2 Jumbo prefixes, but because those make some awkward edge cases that don't currently want to deal with. So it's a little bit fixed in this sense. So the immediate fields are concatenated in high to low ordering, though the instruction words themselves are a little Indian, so it's kind of backwards in this sense, but it's possibly a little bit of a wonky seeming ordering, but it doesn't actually really hurt like it costs that much to decode it that way. So that's kind of why it's being done this way. Yeah, and the 33-bit immediate case is basically a 32-bit immediate, which with a 0 or 1 extension to 64 bits. So this can be noted if one, just takes note of how many bit positions are here in the I field. It works out to 32, and then you have your E field, which will will contribute an additional I bit, which is the 33 bit extension. Yeah, the reason for 33 bits is partly because that's the width that the current CPU core implementation is using internally, and it seemed reasonable enough. This would be more expensive to make everything support a 64-bit immediate, and actually to support these 64-bit immediate instructions, it's actually using two lanes or multiple lanes glued together in order to actually produce the 64-bit immediate field. So that's another special case. Actually, I forgot to mention it here, but actually I forgot to list it, but there's actually a 56-bit immediate that does contain two jumbo prefixes in an F2 block. So, yeah, there's a 56-bit case, but I forgot about that. Or, it's actually 57 sign extend, but yeah, it exists. I just forgot about it. Well, yeah, more or less. Anything else? I'm thinking. Yeah, I think I've said what I've intended to say. So